Hey guys, I just wanted to go over this assignment with you because it is a little rough. Definitely university level, and university stuff is nothing to sneeze at. All right, so first question. We're going to find the cross product A cross B if A is 3i minus 2k. Keep in mind, hopefully remember this, but I is just a unit vector in the x direction. Unit just means length 1. J is a unit vector, length 1 vector in the y direction, the plus y direction, and K is a length 1 vector, ooh, look at that beautiful hat, in the z direction. So this is just a way to do, say, what's your x component, what's your z component. If it doesn't mention a j, that means that's just 0. So not too bad. All right, so we're doing A cross B, so we do our, lay it out. 3 is my x component, 0 is my y component for A, and -2 is my z component, and we have a -1 for our y component for B, and 1 for z component for B. So we're going to cross this. Hopefully you know how to cross. Anyway, you get this guy. This times this minus this times this, and then this times this minus this times this, and then for the k component, this times this minus this times that. All right, so that's not the interesting part. We've done that before. Now we want to use it. So using this result, find the magnetic force in a particle with charge -4 coulombs moving at a velocity of something that looks an awful lot like A in a magnetic field that looks an awful lot like B. Never know. If you check out your AP data pages, notice that your formula is Q equals V cross B. And so that's exactly what we're going to do. But we already have V cross B right here. This is V cross B there. And so it's just the coulombs times that. It's sort of feeding the chicken style. So -4 times -2 is 8, -4 times -3 is 12, and -4 times -3 is 12. And that's it. That's our force in component form. Hopefully that helped. Hopefully, I was hoping you'd be able to get this guy. Some of the other ones are much more brutal, but that was not terrible. Next guy, we got a particle with charge -2 coulombs moves in the plus y direction at 4 meters per second in a region where the electric, I didn't even finish this, where the electric field is +2 newtons per coulomb and B equals -1 Tesla in the x direction. So what I found is the magnetic force. To find the net force, you'd have to do sort of big minus small. Actually, never mind. They will add up. So I need to add 4 to my answer. So it'll be minus 12k. Anyway, so I wanted to show you that there are 2 ways to do this problem. You can do it in a more traditional way like we've done before. We can do our QV's sine theta. Though sine theta, it's just going to be 90 degrees because we've got our velocity in the plus y direction and our magnetic field in the minus x direction. So they're 90 degrees to each other, so sine of 90 is just 1. So just QVB, and then we can use the third right-hand rule to figure out direction. Here's our kind of like x, y, z graph. This is always how you set it up, x, y, and then z. Yeah, memorize what this looks like because that'll be important. Anyway, so we got our magnetic field in the negative x direction. Our velocity is in the plus y direction, but it's negative. So remember with the right-hand rule, we kind of flip the direction. We point our thumb in the opposite direction of the velocity if it's negative. And so if we do this, notice our palm would be pointing in the direction of the negative z-axis. So yeah, that's one way to solve for it. We just do 2 times 4 times 1, made them all positive, and then used right-hand rule to figure out direction. Worked great. We got -8 newtons 8 newtons in the negative k direction, negative z direction. The other way we can do it is we can just totally do Q is V cross B, which actually works really well because we don't need any right-hand rules. We don't have to draw this out. I mean, this works not bad if it's all drawn out, but if it's not, this is a great way to do it. Given that K is 0, 0 here for both vectors, it's 0 for both vectors. Basically, any of the other vectors, like there's going to be no I component. Basically, if you would calculate an ith component or a jth component, and as part of that, you'd need to involve like 2 vertical zeros, that component's going to be 0, guaranteed. Because both, you know, it's kind of like A times B minus C times D or whatever. There's going to be 1 0 in each. So, or A times C minus B times D. There's going to be 1 0 in each of those terms, and so the whole thing will be 0. So the only term we have left is K, and we get that with 0 times 0 minus 4 times -1, so it's just 4. 4 in the K direction, multiplied by -2, we get -8 in the K direction. So either way works. One thing I also forgot to do was add the electric component, but that's pretty easy. It's just electric field strength times the, oh, hold up, never mind. That's in the, no, it's in the positive J direction. Yeah. So it would be minus 8K minus, you got minus 2 times 2. So it would be minus 4J hat. So here's your electric contribution. It'll push it in the negative y-axis. The electric force would try and push it this way because you've got an electric field going this way, and it's a negative particle, so it'll be pushed the other way. Yeah. So that's that. So we got a -8 component due to the magnetic force and a -4 component in the y direction for the electric force. All right, hopefully that helped. Next guy, we got this electron that has velocity 2 times 10 to the 6 I plus 3 times 10 to the 6 J. So really fast. Anyway, it's moving through a uniform magnetic field, which with this strength in these directions. If we want to find the force, we just do again our Q V cross B. It's an electron, so it's -1.6 times 10 to -19 for Q, and then we can do V cross B. Notice there is no K component again, so again our answer will only be in the K direction. Because both of them don't have K. Since the answer to the cross product, the solution or whatever, has to be perpendicular to both vectors, and they're both in this kind of XY plane, guaranteed the vector that is perpendicular to both has to be not in that plane. It's got to be coming straight out in the z-axis, either the positive z-axis or the negative z-axis. Anyway, do that, you get your answer. Not too bad, and it's exactly the same for a proton, except instead of -1.6 times 10 to -19 for Q, you've got 1.6 times 10 to -19. So it's exactly the same, but now it's going in the negative z direction. That's about it for that guy. We probably could have used basically this strategy as well, because we have two vectors in the same plane, but it wouldn't be as easy to figure out the angle they have with each other. All right, now we get into some beefy boys. We got to use calc here and cross product, which will be a delight. It actually doesn't end up being as terrible as you think. But anyway, we've got a wire along the y-axis in a magnetic field that varies depending on where you are in the y-axis. So that's fun. Anyway, we basically just set it up like you'd imagine you would. You've got your current, which notice I converted to amps from milliamps, and then multiplied by the integral of the change in length, like a little tiny piece of length crossed with the magnetic field. But a little tiny piece of length is the same as a little tiny distance in the y direction, so we can just do that. It's got no I component, no k component, so those are just zeros. And then we just put b in its form with its y's in there. We solve. We're only going to have a k component, which is nice, which I guess I forgot to put in there. Oop. My bad. All this in the k direction. K direction. K direction. So yeah, and then we just take our definite integral with these bounds of the answer to our cross product, which ends up being a nice 0.3y dy. Integrate that, we increase our exponent by 1 and then divide by the new exponent. Pretty easy that. Plug it in your calculator. When y is 0, it's just 0. So basically you just want to solve for it at 0.245 meters. And then you get this sucker. That's it. Hopefully that helps. And then I believe this is the last one. Yeah, this next one is the last one I'm doing this video. You've got an electron moving through a uniform magnetic field given by this sucker. It's got this term we don't know for B. Maybe we should leave it in there and just do a cross product, and we might be able to solve at the end of it all. One thing that simplifies matters a lot, I found, is your elementary charge is 1.6 times 10 to the negative 19. But one thing I noticed is this magnetic force is 6.4 times 10 to the negative 19, which is just 4 times the elementary charge. So if I just say it's, or I guess negative 4 times the elementary charge for an electron. So if I write it like this, I can cancel out my e's right away, and that makes my numbers a lot easier, and that helped me solve it. You can still do it without it. It's just not as easy to do in your head. Anyway, if you left the number there, so instead of negative 4 times e, you could have just put 6.4 times 10 to the negative 19, and here you could just put negative 1.6 times 10 to the negative 19. And it would also work, but not be as pretty. Anyway, we do our lovely cross product, and again, since neither of them have a k component, guaranteed that's going to be the direction of the answer. It's either going to be in the positive z-axis or negative z-axis, because it's got to be perpendicular to the plane defined by these two vectors, which are both in the xy plane. So yeah. Anyway, you calculate it out. You got 6b from this guy minus 4b here, which is just 2b, all in the k direction, equaling negative 4k. And so if you just solve, you get negative 2 Teslas is b, bx, negative 2 Teslas. So hopefully that helps. And then we'll do the other one next time. Thanks for listening. I know it's a long haul. Sorry about that.